one resulting vector, one resulting electronegativity polarity to this thing? No, they all cancel out. So this is a non-polar structure. Even though it's got polar bonds in it, they cancel out, so it's non-polar. So that's the kind of symmetry I'm talking about, which I mentioned on the other page. Symmetrical molecules, as long as the peripheral atoms are all the same, they won't be polar. They'll cancel out. Questions about that? So because this is square planar, it's not polar. She thinks she lives here and can just dump anything anywhere. Sorry about that.
Too expensive for me.
Okay, so the next one is TEF4. Question, is this a polar or non-polar? True? True. Where'd that come from? Peru. You know Saruni is a senior?
Yeah. The one on the
He's a
tennis team.
goofball. You are too, kind of. A different kind of goofball. Go ahead.
So whenever you see that type of movements, you just say like that dipole, it's on the.
Say it louder.
So whenever you see like that dipole movements or moments.
Dipole moment.
Moments. Okay.
That means is it polar?
Okay.
Okay. Yeah, and that's a great point to bring up too. I didn't mention that to my second and third hour. The official name for a polar molecule is that it has a dipole moment on it. And that just means it has a permanent polarity about it. So yeah, when you see textbook questions, often it'll say which of these has a permanent dipole moment or just a dipole moment. It just means which one is polar. Okay, thanks for asking that. Because did you see that in the book?
No, I just saw it here.
Okay. Oh, you know what? This may have been taken out of the book too. I don't remember. But yeah, a dipole moment just means polar. Yeah.
Is it possible to not have like a dipole moment, but not a permanent dipole moment, or is permanent dipole moment the same thing as just saying dipole moment? Is there like a temporary dipole moment or something like that?
Yes, there is temporary.
Okay. Are we gonna learn about that?
Yes. We talk about London dispersion force, which is a temporary dipole. Yep, we'll get there. So when it says a net dipole moment, it means permanent. Right on.
So, like, do you have to do the dot structures to know the coordination?
You have to. You can't just look at this thing and say, oh, that looks like a coordination number of 6. You have to do the dot structure. Yep. TEF4. TEF4 looks like this. We have our TE in the middle, some F's, and a lone pair. What's the coordination number?
5.
5. So what is the general shape when we have a coordination number of 5?
Teeter-totter. Or well.
Trigonal pyramid.
Yeah, well, the general shape is a trigonal bipyramid. But you're right, Vinny, that is what, because when we have to take one of our bonds off, it's a seesaw shape. Yep. Let me just show you this so you can have it. Remember, this is the shape in which we have one above, one below, and then 3 along the waistline, like this. Right? You got, oh, I'm spinning too fast. So you have the trigonal bipyramid shape. One of these has to get pulled off. I'm going to go ahead and put the atoms on here so that you can see it better. Okay, so one of these is present, the orbital is present with the electrons, but they're a non-bonding pair of electrons. So this is where we have our teeter-totter, seesaw shape. Is this a polar molecule?
Yes. Oh wait.
Here's our tellurium, the TE in the middle. We have a flow of electrons toward the fluorine. I'm going to just set it to the side like this so it looks like a teeter-totter. And then we have the one to the left. Those kind of cancel out because they're 180 degrees from each other. But then the base of the teeter-totter, those are 120 degrees from each other going down like this. And then there's a lone pair up there. Do the polar bonds cancel out?
No.
No, they don't cancel out. This is a polar molecule. I paused when all of you said yes just to make sure that you were confident in your answer.
even I said don't trust his
Yeah, I heard you say that. I heard you. Trust yourself. So yeah, if I could show you like this, these two that are all in the straight line, they cancel out. But we have the electrons being pulled down this way and pulled down this way. Is there one general area where it's kind of electron rich? Yeah, down in here. Down in there, it's electron rich. And therefore, up above here is where the electrons are being pulled from, and so up here is positive. Which is a little bit weird too if you think about it, because what is up here? There's a lone pair of electrons. So it's like there's this negative cloud up here. However, since the TE is losing its electrons down here, even though there's a lone pair of electrons up here, it does make this region positively charged. It's losing electrons. So this is polar. Seesaw shape. Let's go on to the next one. SeO3 is a simpler molecule. Here's the Lewis structure for SeO3. We have 3 O's, one of them is double bonded, the other 2 are single bonded. When you have a double bond on one of the oxygens, but it could be on other oxygens as well, what issue does that bring up? It starts with R.
Resonance.
Thank you. That's a resonance structure. This guy. That's great, Mohammed. That double bond could be there or there. The bond order we would consider in this case is 4/3 or 1 1/3. It's a 1 1/3 bond order, which means that there's 3 different structures that we could have and 4 bonds to accomplish that in. So the bond order is 4 divided by 3, which is 1 1/3. It's like each of these are 1 1/3 bonds. What is the shape of that molecule?
Trigonal planar.
Coordination number 3, trigonal plane. Right. So the orbitals are like this. This is the SeO3. Is there a net dipole moment? Is there one side of this thing? So first of all, I should say, are there any polar bonds in this molecule?
Yeah.
Selenium, oxygen. Well, yeah, the oxygen is present. So the oxygens are yanking the electrons away from the selenium. Is there one side of this thing that we would say, oh, oops. Now there is. Is there one side of this where the electrons are being pulled?
No.
Because they're all 120 degrees? No, there's not one negative side and one positive side. Yeah, all around is negative, and then the middle is kind of positive. But you need the opposite ends of the molecule. Yeah, you need to have opposite ends. So look at this. Watch, look up here for a second. This is non-polar because all the angles are 120 and it's symmetrical. What if I do this and it's bent?
Now it's
And
polar.
that's SE and O's.
Now it's polar.
This is polar. These do not cancel out because you have electrons coming down here and down here. So down in here, we're electron rich, and up in here, it's electron deficient. Now that's not the case. This is non-polar.
So the double bond has nothing to do with it.
Correct. The double bond has nothing to do with it. Okay? Don't let the double bond influence your decision as to whether something is polar or not. Ever. The double bond has nothing to do with it. Yes, sir.
Now say that you do have like a double bond to a similar, like, say you have a double bond versus a single bond and they're asking you which one has a larger polarity. Is it going to be the double bond with the more polarity?
We don't think of it like this. No.
Okay, so it's based on which atom.
Just the electronegativity, yeah.
Yeah.
Yes. No.
So even if it's a double bond, that'd be trigonal plane.
Yeah, there really isn't a double bond though. These are all really the same. 1 1/3, 1 1/3, 1 1/3, right? Because it's a resonance structure. Prox.
Rare question, eh? So the shape balances out.
Right, that's right. If it has that symmetry, total symmetry. Okay, so can we generalize something? Yeah, not yet. We can't generalize yet. Let's go to the next one. CH2Cl2. Dot structure on this one is easy. It looks like this. C with 2 H's and 2 Cl's.
Oh no.
Wait, but the CL.
What are you saying? You giving it a yes or a no? Yes, polar? No, not polar.
No,
Wait,
not
how-
polar.
Oh, I have
CL's
messages.
cancel out?
Hi. Whoa, there's.
A devil?
Like, no, it
I
was
don't
a
want that
smiley
devil.
face.
Yeah,
It was a
that's
smiley
fine.
face first, and then she added the
And it made
devil.
it creepy.
Yeah, with those eyebrows, I saw.
Yeah.
It was, I only drew the smiley face. She ruined it.
No, I said it's a devil. An onion.
What she does.
Wait, what are the CLs cancel out?
All right, now let's take a look at the way the dot structure is written, and then let's look at, well, first of all, what is the shape of this molecule?
Tetrahedral.
Coordination number of 4, and they're all being occupied by bonds, so it's the tetrahedral molecule. Okay, so is this, what I have written in red, is that different from what's in green?
Very much so.
Is there a difference between these two?
Yeah,
Very
that's
much
orgo.
so.
Okay,
I'm
you
kidding.
say yes.
I'm kidding.
Now look
No,
at my
there
model.
isn't. There isn't.
We have 2 adjacent CLs and 2 adjacent H's. Okay, so if maybe I'll switch the H with the CL. Now what? Oh gosh, I still have 2 adjacent CLs and 2 adjacent H's. You can't rearrange these things to not have 2 CLs together. So it doesn't matter how you write the dot structure. You need to understand what the shape looks like. You might look at this and say, oh, well, they all cancel out because they're 180 degrees from each other. The CLs are and the H's are. Nope. What's happening here? Now, I have different size atoms, the bigger ones on the CL. So this carbon to hydrogen bond, which is those, that's not polar. They don't have a big difference in electronegativity. It's a non-polar bond. But these bonds are polar. Carbon to Cl are polar. So the electrons are being pulled up toward that Cl and up toward that Cl. Is this a region that's got, or is there electron rich region? Yeah, right up in there. This is polar.
So, because there's like the H, that we can say that it's like
Yeah. The only way they can cancel out is if all the peripheral atoms are the same. You can look at this immediately and say, oh, they're not all the same. It's not a symmetrical molecule.
Because of the sun. Or
Because
never mind.
the only way they can all cancel out, remember, think of it like vectors. This has a vector going that way, that has a vector going this way. Since that's not polar, there's no vector at all down here. So you got that and that. Overall, you got the resulting up vector. Yeah. That okay?
So, it doesn't cancel out.
Right, they don't cancel out, therefore this is polar.
Oh, alright.
It's polar. Yep. Everybody okay with that?
Yeah.
Good. So it makes no difference how you write the dot structure for a compound. This and this are the same thing. Because in reality, when you have a tetrahedron, one is next to all 3 the same way. Because look, you got 1, and then the other 3 are all kind of equally distributed around it. 2 more. I give you a lot of examples on this because it's very confusing. And if you don't think it's confusing, you haven't practiced enough yet, because you'll find that it's confusing. PCl3 is our next one. How was I doing this? I'll do this over here. PCl3 looks like this. Coordination number is what?
3, 4.
4. What's the shape of this one? It's a trigonal pyramid, that's right. Trigonal pyramid. That lone pair is pushing down on these, causing them to all be down. So it really just looks like this. Let me change for a little one again. Here's our trigonal pyramid with the P up above, and then the CLs are all pulling the electrons out. Are these polar bonds?
Absolutely.
P and CL? You got the CL in there, yeah, it's polar. Lena? Nope. Coordination number of 4 means that they have a 109.5 degree angle. But we have a lone pair spreading out, squeezing 107. 107. Yep. The 118 is the coordination number of 3. Polar or non-polar?
Polar.
Yep. The electrons are being pulled up, up, and up. So up here is electron rich, down here is electron deficient. Yes?
How come for A, for xenon, there's like the long pairs, but they don't split
Right. Because they're repelling equally. Above and below. Yeah, so this is when it's a square planar molecule. I wrote it kind of like this to kind of show up like that, where you have a lone pair above and a lone pair below. Now you have a lone pair above. It's